Awesome. Okay, so I said this is going to be interactive. I promise I won't ask for too much participation from everybody who wants to remain a bit quiet, but it's going to help craft a better experience over these next 90 minutes, I promise. So like the talk title promises, I want to be able to get you up to speed with AI and ML in 2020. I know AI and ML are just two acronyms that are part of a very large set of buzzwords that you're probably very used to hearing, but I hope that by the end of this talk, whether you have never tried to grapple with AI ML before, or if this is something that you're pretty familiar with and want to know some tips and tricks, I think this talk will have something for everybody. So kicking things off, a little bit about myself. My name is Nick Walsh. Like was mentioned by Leah in the beginning, I am a developer advocate at Amazon Web Services. I don't know how many people have heard of Amazon Web Services, but the idea is essentially we help to manage cloud computing. And if you run applications, we likely have services that can help you. I'm not focusing today's talk on AWS. That's what I spend most of my day job doing. But there are some examples and scenarios where using building blocks from AWS will make it easier. Developer advocates do lots of things. I'm sure many of you folks have interacted with folks that have a similar title. So you're probably pretty familiar with people just like myself. Formally, I am trained in biomedical engineering and math and statistics. So a lot of people are probably wondering how I ended up in computer science and AI and ML. It was a long journey with lots of different hops along the way, but you'd be surprised if I really look back, I was doing really, really basic forms of machine learning back with like linear regression and stats, even when I was doing research very early on in college. So it all sort of dovetailed eventually. I've worked at some other companies before AWS, Wolfram, Datmo, MLH actually is one of them, and I did medical research way back in the day in dermatology and neurology. I know all these things sound very disconnected, but when you work in the business of numbers and math, there's always some line of continuity. But most effectively to this conversation, actually, when I was at MLH, I worked as a coach. So many of you are probably familiar of the coaches program through Major League Hacking. I did that for many years. That was really awesome. I loved helping out at hackathons and giving talks and enabling developers. So this is right up that same alley. And that's a big reason why I love my job now. I play a lot of games and I love New York. Born here, grew up here, went to college in New York. Very happy to be back. I don't know. There's lots of things that make New York great. I won't delve too deep on it. I want to make sure that y'all can get to the content. So I'll spare you that story for another time. So this talk, like I said, it's going to be a little unique in that this is a bit of like a choose your own adventure. Now I don't know how this is going to go, given that we have a room full of people. I know a few of you have your videos on and a few of you do not. So I'm going to see like if you can add in chat, if there's anything that's super interesting to you, numbers 1 through 6, you can post like a bunch of numbers in like one line. I just want to gauge to make sure that I cover the things that you all care about. And if no one posts a certain number, I don't want to end up getting to it. And I don't want you to have to like jump in and like gavel me down midway through. So if you're in the Zoom call, you can just post about the things that interest you the most. And I'll try and keep an eye on that. Leah, actually, I'm having a hard time pulling the Zoom chat up. Total.
Yeah, no, I can watch it as those are coming in. So,
Cool.
And also I can jump into with any questions if you're unable to see it, and I can ask those for our fellows. But yes, if anyone can throw in, your numbers. We have, looks like 1, 3, and 4 are pretty popular.
Cool.
We're getting ones for everyone so far, every number, but 1, 3, and 4 are definitely the most popular ones.
Awesome. And you all have some time to fill that in. Oh, I think I have a pop-up over here for chat. Does this show the chat on when I'm screen sharing? Probably not, right? Because it's the window. Oh, nope. Cool. So I can keep that up. Awesome. So lots of interest all around. Cool. Another thing is that please interrupt me. Like I'll watch chat now that I have this up on my screen. If you have a question about something I'm explaining or you want more detail on it and I go past it, just like yell at me in chat and I'll go back and we'll talk about that longer. I'm also going to do Q&A at the end. I have this full time blocked out. I think it was 90 minutes. So I will stay for the entirety of this. The goal here for this entire talk is also like, I want to talk at you for a little bit because I think that's a productive way to sort of fill your brains with information. But most importantly, I know a lot of you are going to approach this talk with a different sort of set of context and a different set of questions. I want to make sure we have time to answer all of those questions together, which is why I selected 90 minutes. We're probably only going to have closer to like 45, 60 of direct content, but there's a lot of fun tangents we can go down involving AI, ML, and I wanted to make sure you all had that opportunity here. Cool. So choose your own adventure. We've got a handful of different things here in this table of contents. Thank you all for the participation so far. I'm not going to go through all of these right now because I'm about to just dive into them. One was very popular. So this is, I guess, what we'll start with here. So if we start off with AI and ML fundamentals, there are a few more buzzwords that I think are popular to bring into the discussion here because it'll help to situate ourselves a little bit. And this should be familiar to a lot of folks. So a lot of people have heard of machine learning. Largely, I classify machine learning as the ability of a system to learn rules. And this starts to make sense when we compare this to the superset of artificial intelligence. Now, a lot of these terms are often used interchangeably because in many of the times where they're used, they may be interchangeable. To be quite clear, all machine learning is artificial intelligence, but not all artificial intelligence. Am I mixing that up? Machine learning is the smaller set. Artificial intelligence is the larger set. Essentially what this means is if you're doing machine learning, you're definitely doing artificial intelligence. If you're doing artificial intelligence, it doesn't necessarily mean you're doing machine learning. I know people like to be armchair analysts on Twitter and what have you, or Hacker News, or pick your poison. But like quite literally by definition, artificial intelligence is simply the ability to make decisions in a programmatic way. You can think of any system you write that has a function that accepts inputs and conditionally performs some sort of output as artificial intelligence. Like I know the big joke is like, blah, blah, blah technology is just nested if statements. And the reality is that like nested if statements are a basic form of artificial intelligence with a very primitive and inefficient way of crafting those rules. Machine learning develops systems that remove the requirement for you as a user to write and craft those if statements. You can simply hand it a pile of data and it will, through the use of an algorithm, figure out how to craft those rules. So that's where machine learning becomes a real step up in terms of efficiency and effectiveness from artificial intelligence. Again, these are sort of nested dolls of classification. These are not separate things, which is why it can be very confusing. Now, another step deeper, not to use a pun, but like deep learning is if we were to say that machine learning is the ability to learn rules or to create those nested if statements, deep learning can do something sort of another level higher. Deep learning can, through a very nuanced form of machine learning, through convolution, through neural nets and a broad class of, we can call them algorithms here, or network architectures, can start to learn, in air quotes, properties about an object where we tag it with a particular label. Like, for example, we can tag an image as a cat, but what deep learning seeks to learn is that certain aspects of an image that we may pass it would be conducive to the cat label. And this can extend out to many different objects. So there's a whole field of trying to have insight into how deep learning models learn and representing that to be able to assess things like bias and generalizability. But ultimately, when we think about this, we're broadening the scope, but as we go more narrow in these classification tools, from artificial intelligence down to deep learning, we essentially broaden the ability of what the machine learning system or what the AI system is actually able to do. So when we get all the way down to deep learning, we don't have to tell it that a cat is defined by ears or something, and its tail and its shape and so on compared to a dog. It will identify these features inherently to it. And this comes into play with a lot of things like computer vision and so on. Cool. So I mentioned this sort of at a glance before, but I define machine learning, and I'm not an expert, so don't like quote me in your reports. I don't have a PhD, but it's most easily understood by me with this definition. So it's a process in which a computer system makes decisions based on rules and policies that it learned on its own. I mentioned that AI can be a bunch of if statements. So if we tacked off the learned on its own part, then we would be an AI system. But if you implement a system that can learn from data or learn on its own with data, which we'll show in just a second, then that's where we start entering machine learning. So anyone who has started to work with machine learning has started to grapple with these three separate problem spaces. Depending on how you classify some of these things, there's parts of overlap essentially, or there's like ways to sort of finagle around how you define reinforcement learning with some other examples, but largely you have these three separate sort of spaces. The biggest difference that I think you'll likely find is supervised versus unsupervised learning algorithms, or supervised versus unsupervised problems. So an example of unsupervised machine learning, I'm doing a faux pas and starting in the middle here instead of the left. It's ultimately where an algorithm will find trends in the data and will surface insights irrespective of any intent of you as the user. So what do I mean by this? oftentimes algorithms that are unsupervised, well, all of the time, unsupervised algorithms do not require additional user input outside of the data set itself to ascribe additional insights. So for example, if I were to pass in a bunch of images, like a corpus of 1,000 images, and let's say that we know that there are a bunch of cats and a bunch of dogs in this data set, but we simply passed in a folder of images. We did not assign labels to the images that were cats, and we did not assign labels to the images that said dogs that designated them as such. If we ran something like a clustering algorithm on those images, you would likely find that due to the inherent properties in that algorithm, in those images, the clustering algorithm would pile the set of images into largely two clusters. Now there's some trickery we can do and knob tuning can do around how it defines like requirements and tightness of those clusters. But the idea here is that we did not have to tell it, how many groups we have. The job is to simply surface this insight that in our corpus of data, we may have two. Now, this is a trivial example when we have a known data set of cats and dogs, but let's say we have a data set that just has, uploads for images from our users. We want to understand how many different groups of user behaviors there are, or types of images that are uploaded. A clustering algorithm on hundreds of thousands of images could surface some really interesting insights here. So again, this is more about surfacing knowledge than it is about being prescriptive about anything in particular. Now, the inverse of that, I don't know if it's the technical term would be inverse, but the sibling to that would be supervised learning. So let's go back to the cats and dogs scenario. What you would want to pass in is not just the image data itself, but you would tell a supervised learning algorithm, hey, this set of images is belonging to class dog. This other set of images belongs to class cat. And this additional parameter that you're passing in with the raw data is called the label. So this is a big step up. In unsupervised learning, you don't have labels, and in supervised learning, you do have labels. The goal of supervised learning systems is often to take in a new image that is unlabeled. Typically, let's say it's from a user or your application in production. And then what happens is you want the model that you've trained to be able to predict whether that new piece of data is closest to one class or another. Or maybe you have multiple classes and you want to predict what class it is closest to. I'll go over the word class because that can be used in a lot of different scenarios, whether you have numerical data or visual data or what have you. Now, this last class over here is something that has picked up a lot of speed and I guess popularity in recent years, and it's reinforcement learning. So this often involves a very complex problem and reward space. It is not simply as discrete as this image, which is a static piece of data, has this discrete label, which we could say is cat or dog. It typically involves a sequence of actions. So even though I guess you could say that a sequence of actions is a static piece of data, it often revolves evolution over multiple points in time. And what this results in is some sort of model where you maybe have a large variance in all of the behaviors that can be performed before you're, let's say, trying to reward an ideal agent in this situation. I know that was a lot of buzzwords and it's kind of tough to understand this, but I think the examples actually make it much more tangible. So in reinforcement learning, this would be applicable to something like a self-driving car. Now, there are a lot of systems in self-driving cars, some of which involve supervised and unsupervised, and some of which involve reinforcement learning, but largely the biggest example that defines reinforcement learning with self-driving cars would be the idea that you have a long time span for which you receive reward. So an example of this would be, let's say you want to drive from your house to school. The reward that the scenario that you want to reward is driving there without accidents. That, let's say that's binary, right? That any accident would be unsatisfactory. But then there's a whole set of other constraints that you can impose or want to incentivize, behaviors you want to incentivize, like stopping gracefully, starting gracefully. These are things that, like if it's just a robot and there's no humans in the car, they may not care about that. But we need to come up with some way of rewarding these behaviors that we want to see in the agent. And we can typically model this out through simulations. I'll talk a little bit about a really popular example about this later, but it's really complex and people do entire PhDs on algorithms for any one of these. If you can understand sort of the broad strokes of what makes them different and use cases for each, you've definitely come out with more than enough. Okay, I clicked over in chat. There we go. So supervised learning, again, to reiterate, it involves a pre-existing data set and it has labels. Now, we're going to walk through a scenario by which we can essentially craft this. This is going to be all of the building blocks of a supervised learning system where, let's say you work at a company, you said, I want to implement machine learning. Unfortunately, it's not just a little bit of like salt you can sprinkle on your application. It doesn't work that way. You have to be a little bit deliberate with it if you want to achieve value at some point. So first, you're going to start off with a problem statement. Then we're going to go into what training looks like. I know this is a big elephant in the room. And then lastly, inference. This process is consistent no matter what domain you're in. So what subject matter or type of customer you have, or what type of algorithms you're going to use within supervised learning. Additionally, even if you don't have labeled data, this training step here, if you cross out the parentheses there, would also be applicable to unsupervised learning as well. Okay. So the first thing you need to understand is, what am I trying to solve for? An example that I gave before was classifying an image, dog or cat. So let's say I have a repository of images, and I as a human can trudge through them and say, okay, this is a dog, this is a cat, and so on and so forth ad infinitum. Now, as you have a production application, you may want to automate this process, right? You may not you may require that result or that decision in real time, but you may not want to have a human sitting there on staff waiting for like an email to pop up in their inbox to have them label. And so we want to build an AI system to solve that and to essentially automate one of the very common value propositions of using a model. So I used scary italicized text here because I'm a math nerd. But essentially, when we're creating a model, we need to perform training. This is a necessary step. This is also one of the more expensive steps, especially early on if you're just experimenting with AI and machine learning. Essentially, you start with data here on the left-hand side. You want to get out a model. This is an entity that will make decisions. We'll dive a little bit deeper into that in a second. But the way you arrive at a model is by passing data into a particular algorithm, and the result of the algorithm completing its computational steps is going to be a model. So to make this a little bit more clear, we're going to go through this with a set of diagrams here on the right. So each one of these different squares that you see contains the exact same set of data. So in this first slide, all I want you to look at is data. I have that circled. And I have data of two classes. I pulled this side from another deck, so it says cheaters and non-cheaters. But let's say it's cats and dogs, right? Let's say cats are red and dogs are blue. So this is a supervised learning scenario. I have a folder full of dogs and a folder full of images. And the way we can pass in labels depends on the algorithm, but largely you generate what's called a manifest. This can just be a giant configuration file where you basically say, okay, all images in this folder are class 1, and you can add a label like dogs, and all images in this second folder are class 2, cats, for example. You can extend that out if you want to have a multi-classifier for a bunch of animals. So something that was really hard for me to grasp in the beginning, but largely involves a little bit of faith unless you want to get really, really, really deep into the math, is this concept called dimensionality reduction. So you're probably wondering, Nick, you said I have a bunch of images. How do I have this really nice and pretty X and Y axis over here, or a set of X and Y axes with these dots on it? How do I get from images to that? Well, that's a great question, Nick. So the way you sort of arrive at that is through dimensionality reduction. This is a mathematical technique that has been used in modeling broadly, even separate from machine learning, for many, many, many years. Essentially, it is a set of statistical tools that will help to take your data that can exist in n dimensions. So here we see X and Y, but let's say you're dealing with, images, for example. Your images can be reduced mathematically to RGB values at every single pixel. And then let's say we can flatten them all out. Now you have n times or x times y number of dimensions, and each of those dimensions has one value. This is like some absurd graph that you can't even actually visualize yourself. There are statistical tools that help to essentially suss out the most causal features amongst those images that can, let's say, for modeling, account for the difference in between the classes, for example. There are a handful of known ones that work really well. Things like LDA, latent Dirichlet allocation, I believe. A lot of this starts to be done automatically, so you may not even need to visualize something like this. These sometimes are built into pre-processing or algorithm steps for the machine learning training. But when you're trying to visualize your data, this is really important. I think the other thing to sort of add on here, and I'm sorry because I've added a ton of additional theory and context on this single slide, is that these problems become linearly differentiable. Or partially linearly differentiable, and this is a really mathy term that basically means that, like, can you draw a line or a plane being either in 2 dimensions or 3 dimensions or n dimensions that separates your data into multiple classes. We'll see that why this comes into play when we talk about how we actually like get inferences out of our model. But essentially, in very plain non-math terms, the idea should be, how can I draw a line, and line not being necessarily a straight line, between my pieces of data, such that on one side of the line I make one decision, and on another side of the line I make a different decision. This is sort of the primary crux of what the model does, but we'll see that in just a moment. Okay, so this is the model decision boundary. This does what I was just speaking about. Essentially, in each of these different squares we see here, each of these is a different resulting model from the same set of data. Now, how did we get there? We got there because we have different algorithms. Now, when we understand the decision boundary, like I said before, on one side of the decision boundary, we want the model to guess that a new piece of data that falls there would be one category, and on the other side, we would guess that it would be another, that it would be the blue category, for example. So the algorithm actually doesn't have a visual representation here in the graph because it is the process by which this set of data arrives at that decision boundary. So I mentioned before that the difference between AI and machine learning is that in machine learning, the system can decide for itself what those rules are. Now here, this is each of these decision boundaries is a different resulting output from different algorithms on the exact same set of data. So if we were to look at the decision tree in the top left, let's say, for example, we made like 1 or 2 if statements. We made like a one nested if statement, like, oh, if like, you know, if, and it's tough because like tail is not an entity, but like, you know, like if this parameter is like, you know, over this value, then it must be a dog, else if this thing, then it's cat or something. And you know, you have this very basic tree. Well, like that kind of makes sense, but like, I'm assuming that everyone who looks at that can say like, I think there's a better way we could do that, make it a little more accurate, and probably would be really painful to try and perform that analysis, especially if we got a bunch of other animals or a bunch of different classes involved. We see the basic logistic regression. If any of you have taken probable or basic statistics classes, you'll probably have seen that before. And then as we get down here, SVM, neural network, random forest, these are other more advanced algorithms and processing techniques, neural networks going, you know, a little bit down into deep learning with how we can perform this modeling act. I know modeling is a term that's used heavily in statistics. Well, that's not accidental. Modeling in statistics has been around for a very, very long time. How we can perform inference and fit curves to pieces of data, and machine learning has made that much more popular and in the forefront here today. Even here over in random forest, we can see that there's like this, I guess it might be fully encapsulated data point that can have its own little realm here, even beyond a different line here. And this is why I say that, you know, linearly differentiable doesn't necessarily mean one plane. It could be another encapsulated part of the plane. And so all of this to say that each of these algorithms is an opinionated take on how to separate this data. So each of these algorithms has inherent trade-offs, whether that be how long they take to run, like how computationally intensive they are, how they scale with the size of your data set, some of their abilities to handle class imbalances, like in a fraud scenario. Maybe you're a credit card or a financial company. 99.9% of your transactions may be known to be valid and not fraudulent. 0.1% could be fraudulent. That can be a very difficult problem in machine learning, and some algorithms may be better at handling data that looks like that. So there's trade-offs to all these algorithms, but I don't want you to be scared of that word because I know it can seem very tricky, but largely think of it as a function that you're putting your data into. It will result in a model, and there's trade-offs to each of them. And there's been a very large push to understand those trade-offs, even if you are not sort of in the weeds with, you know, having to deal with the math and the nuts and bolts around that. So each algorithm behaves differently, a lot of stuff I have said. So you're probably all wondering, you've trained your model, how does this work? Do I just get, when I'm done training, do I just get this endpoint that I can throw data at? Do I just get like, does my computer start shooting money out of its like non-existent disk drive or something? Like, unfortunately, it's not that easy. You need to perform something called inference. The easiest way for me to try to describe this, and it's a bit of like not great example, but largely if your machine learning model is just this like set of rules and the ability to perform, like, okay, for a set of input, I can give you an output. It's literally just like a function, right? But that function, like all software, needs to be productionalized. You have to find a way to put it behind an API so that it can talk to either other internal systems or external systems. Then you need to manage all of the traditional problems with software around deploying that, version controlling it, and so on and so forth. And there's a lot of unique parts of why that's hard in machine learning, but I'll get into that later in the machine learning and production section. So again, input being data, we feed that into our model, which is sort of this static component. So training completes, it has a discrete endpoint. Then we get this model, and we can now pass in live data that, let's say your user uploads pictures. You don't know if it's cat or dog. You haven't had your employees label that. Now that model can return a prediction with a confidence value of which class it thinks it belongs to. So what does that look like visually on this representation? So this is something that we call a decision space. So if we look inside the same set of graphs, I kept mentioning this before, but essentially the model decision boundary, the purple, this like really ugly set of equations that the model spat out as a result of your training step, is what will determine how new inputs to your system are predicted upon. So when I said before that everything gets squashed down in this race to, like train your model because it needs to have this linearly differentiable problem, this dimensionality reduction has to also happen to the data that you're trying to infer on. This is a sort of subtle point, but all of the steps that you do to prepare your data outside of labeling that data with an actual answer of what class it belongs to, all of those same steps still need to happen to the new data because it's like an equation, right? If your equation takes properties A, B, and C, if you want to run a new piece of data through it, it also needs to have A, B, and C. So we run our data through that. Now, let's say I have this new image. It can fall hypothetically on this two-dimensional set of axes anywhere. Let's say it's very similar to the blue data. It'll likely land somewhere in the bottom left. Can you see my cursor on here? I don't know if that's helpful. I feel weird pointing to my screen and stuff because no one can see that.
Yes, you can see the cursor.
Great, cool. And if I'm going too fast or anything is confusing, again, like any feedback, throw it in chat. We can modify this and run this differently as we want. So let's say I have this new piece of data. It's an image. I don't know what animal is in it. It just got uploaded to my system. Now, when that new image gets squashed down into RGB values, and then it gets squashed into this these arbitrary 2 dimensions, it will fall somewhere on this XY plane. Now, this decision boundary in each of these, these examples grants us a decision space. So if my point, this new arbitrary image, if it gets squashed down to a data point that can be put in this point, like right over here, well, this entire decision space on this side of the model boundary is red. Now, there's like this visualization is not something that gets represented by default from your model. Like when you spit it out, you don't get this like long report about like, hi, this is where it's cats and this is where it's dogs. But this is like why it's difficult to get into AI and machine learning. But understanding this helps give you some insight as to how your models will behave, because a lot of people think it bubbles up to one value around like accuracy, and that could not be further from the point. So let's say we have this new image. It bubbles up to this point here. It is in this red class's decision area. This color is brown, but it should be red. And it would predict, let's say red was cats, right? It would predict cats. Likewise, if it was on this side over here and it was blue, it would predict dogs because that was blue. Now you notice that there's some area all the way up here in the SVM example, a support vector machine. It's a particular type of algorithm that would predict dogs. Whereas over here, the neural network did this, linear type of example or logistic regression, same scenario, where up here, the same exact data point would give a different prediction. Now, the accuracy, which is defined by, how many correct predictions or correct dog predictions it got, for example, may be equal in each of these, but we can definitely see that there's a trade-off amongst them. One sort of qualitative way that a data scientist or a machine learning engineer would look at this would be if you expect dogs to have a high variance in, let's say, the types of dogs and how they appear in your pictures, but cats may be more homogeneous, then this model that sort of intuitively leans more on dogs with a larger decision space may be more ideal. And that's something that may, is very it brings the art into machine learning. There's no explicitly correct answer. It's a trade-off depending on what your organization needs and ultimately how you solve problems for your application. Whereas if you assume that maybe there's like no bias between them, or you need to identify them at exactly equal sort of levels of preference, a model that looks like this may be a little bit better. There's lots of knobs we can actually tune, and I'll get into that in a bit. Another scary word after algorithms is hyperparameters, but I promise that'll be much easier. If you think of these as different opinionated takes on how to, create those rules, hyperparameters are like these fine-tuning steps to how that training process actually occurs. Cool. I don't know if this is out of order. This is out of order, but I think we have more than enough time, and I just said I would get to this eventually, so why don't we get to this now? This is great. This is like playing like Russian roulette with my own slide deck. Okay, so AI ML in production. In this section, what I want to impart a little bit to all of you is sort of the tools, a little bit of the tools, but largely like, actually, give me a sec, because I think one of the other sections makes sense to do before this. This is also a little bit of an overview, but it should be fine. Sorry about that. Quick audible F1 pit stop. We're good. All right, classes of AI problems. I know this one wasn't too popular, but it's also really short. I won't dwell on it too long, but I think it helps to set the stage. So when we're talking about the landscape of AI ML problem solving, these are things you've probably heard a lot about. Again, more buzzwords, but let's lend a little bit more, facts to them. So at the top here, we have computer vision. This one is, I think, like very present in many of our lives, whether it's things like multi-factor authentication or like simply unlocking our phones. Computer vision, whether it's for images or videos, has become ever present. And to be honest, it's really exciting, right? The ability to be able to automate something like image analysis of images is something that's fairly novel. I feel like we're used to this idea of being able to crunch numbers and on like credit card transactions and determine with, graphs how things can be, like fraud or not fraud. That's like a problem that's existed with solutions that have existed forever in our lifetimes. Computer vision very much feels new. And I think that while it has been around for a long time, it has crossed into the boundary of consumer applications directly in your phone or in your hand or in your everyday lives to a much greater extent. Largely the way computer vision is going to work from an ML perspective is like I described before. Machine learning algorithms, even if they accept an image as input, essentially what has to happen is that image has to get broken down into numerical data. So when we think about what actually constitutes an image, you have an X by Y pixel image. It has either an RGB or, I don't know, like CMYK encoding, where it has a value for red, a value for green, a value for blue, and then oftentimes a value for transparency. Oftentimes that's equal for the entire image. And you may think that a machine learning algorithm can just scan across that grid, but that's actually not exactly the input. You don't pass in a two-dimensional grid. You often pass in a one-dimensional vector. And so if you think that like an image is like 1080 pixels wide, like a 1920 pixels wide, once you get to the first pixel on the second line, you actually encode all of that and append that on to the end of this previous sort of vector. And so you're probably wondering, like, Nick, why are you explaining all of this? But when I mentioned before that in an equation, you need to pass in the same set of inputs every single time, one of the things a lot of folks don't realize about computer vision is there's this really intensive pre-processing step where you actually have to scale all of the images in your data set to the same size oftentimes. Because if you consider every one of those pixels to essentially be a feature in your data set or how you want your model to perceive things, you need to perform oftentimes scaling your images down, cropping them and fitting them into this very small or a very small sort of image size. And this is challenging because if you want to blow out the image size, that can drastically increase the amount of computation and costs for training, and may not even be as effective with off-the-shelf solutions. Next up, we have NLP, natural language processing, or NLU, natural language understanding. This is an entire class of machine learning and AI problem solving around language. Now, I know that sounds like kind of obvious, but essentially what this class of research aims to do is to be able to derive insights from text, or to be able to derive sort of higher order intention from text, which is even more difficult. we know tools like, or services and products like Amazon Alexa or the Google Home, Siri, all of these are sort of the productization of NLP and NLU research that has been happening for a very long period at academic institutions, and has now sort of like made its way into the forefront with tools that we use every day. NLP and NLU has this really unique set of problems where, there's this subjectivity to some NLP and NLU that becomes hard to encode. Things like humor, things like satire, being able to understand these intrinsically with the context around just the words on the page is a large class of problems that AI and ML has a difficult problem right now of solving. But for direct sort of understanding intent, what is the main focus of a conversation or a passage, or can we identify key terms? NLP and NLU works on this a lot right now. Next up, we have recommendations. So I know that especially right now, a lot of us are home going on your favorite video platforms of choice, whether it's Amazon Prime Video, Netflix, YouTube, what have you. And from content that you see, or even if you haven't been watching content recently, whenever you open that page or your homepage, you want to see content that you want to watch. You don't want to have to go hunting for it. And ideally, yeah, you'll go and search for something very particular that you want, but you want to be brought recommendations for content that you are likely to enjoy, and not stuff that you don't enjoy. This is a classic problem. Amazon personally has faced this from all the way back during the .com days of when we first started selling books. The idea of how do we surface books to people that they may enjoy, and data that we have had since then would be like books that you've purchased or reviews that you've given. And so there's a whole class of algorithms and problems to more effectively serve recommendations. Now, there is an objective sort of metric you could think about with recommendations, like what percentage of recommendations do you serve are things that your users clicked on, for example, like on the homepage of Netflix or whatever. But the other thing is that it's often very subjective, right? Like just because you liked one movie in a certain genre, there's a parameter about it that may not be intrinsically labeled in your data set that makes it hard for you to serve a recommendation to someone else. Additionally, one of the hardest problems in machine learning can be effectively trying to serve predictions to people when you have a low amount of data on them. So for example, if I've watched no movies at all, I'm a fresh user to, let's say, Netflix, and there's no other data there, it may make sense to simply serve the highest performing movies across my entire platform. Just like all of the top hits, and those are likely to be ones that I may like. But as I start watching movies, like having ratings, maybe I don't rate. Maybe the platform uses data like how long you stay on a video or how many episodes of a series you get through. These can all be used in very nuanced ways to serve you recommendations. Let's say you're on like YouTube and you've subscribed to one user and a different user that has overlap of viewers. You get where I'm going with this. There's lots of really nuanced way to serve these recommendations. Ricky said in chat, YouTube recommended a video of giraffes fighting when he was watching, or when they were watching a coding live stream. Yeah, no, recommendation algorithms behave in really weird ways sometimes, and the AI ML engineers, that's their job to figure out why it does that. But I think this is something that's very visceral to us because as users, recommendations are things that are very tangible to us. Like we're developers, but when you're thinking about implementing AI ML systems, you want to think about how that experience is for your user. Yeah, Ricky, you said you enjoyed the video, so I guess it was a success. I guess so, right? Maybe it was an A/B tester, or sort of a random injected, thing there. But I think there's no better example of this, and I don't know how many of you have faced this, but like, let's say you watched one video one time, you clicked on one YouTube video, and let's say you didn't even like it, right? And you clicked off after like 30 seconds. Now, all of your recommendations are just flooded with that same type of content, right? You're just like, no, please stop, algorithm, stop doing this to me. Or like, let's say you search something on Google and like, every single ad that you ever get from that point forward is the same piece of content or something, right? You're like, no, I can only buy one mattress. Like, why am I continuously getting mattress ads for like 3 months? This is a bad customer experience or a bad user experience. So developing recommendation algorithms that can try and take these scenarios into account are only better for our users. Numerical forecasting. This one is likely, this is a very like sort of mathy oriented one, but this is the most math-like and statistics-like probably of all of these next to anomaly detection. Essentially, this is really big on supply chain. So essentially, based on historical data around things like, let's say, how much energy your company utilized or how much inventory you had during a certain season, and how many sales you had, how much should I expect to need to stock for the next quarter? or how much can I expect my bill to be based on this historical data. Now, this is almost like purely mathematical, and this is often, there are a lot of tools in the space that do this. We'll cover sort of one of them later, but this is one that sort of, out of all of these, probably slips into the background and is typically not as at the forefront with customer-facing features that you would see. Next up is anomaly detection. So this one is really broad. This can take the form of supervised learning, but it's often unsupervised. Essentially, if you think of statistics, this is literally just outliers, right? Can we develop a system that can just like take in all of the data, and based on historical data, we mark, like it will figure out the statistical distribution, and it will tell you when new data that comes into your system is an outlier. Now, this oftentimes is not going to tell you or be prescriptive over whether that outlier is like fraud or something, but you have the peace of mind of knowing, hey, this is something I should probably be looking at for one reason or another. And it sort of takes this intractable problem of like, let's say a Visa or a credit card company looked at every single financial transaction. Like even that is a joke. That would be impossible, right? There's just so many transactions you can't. If you were able to surface, let's say 0.1% are fraudulent, but you were able to surface like 1%, you've now cut your problem space from 100x to like 1x. And maybe that is a human reviewable sort of system where you can prioritize how you view things. And again, not prescriptive, but it can sort of make these problems that are sort of infinitely scalable or uncomputably scalable to something that you can manage. And then last is data synthesis. This one's really exciting, especially recently. I was thinking a lot about how I wanted to describe this one, but there's honestly so much, and especially with the launch of GPT-3 from OpenAI, we can talk about that more in depth there, but essentially using AI and machine learning to pass in training data for media of various types, be it audio, be it images, video, and synthesize new content from that data. So if you're thinking about things like GANs, generative adversarial networks, you're right on the money here. If you're thinking about trying to, and GANs have multiple applications in both images, video, even in audio synthesis. So an example that's really sort of fun and not necessarily a huge business, well, I guess you could use it for business, is like synthesizing music. We think about like all the music that is to be written, it's probably been done in the history of music, but that's not the case, right? Now we have the automatable we have an automatable process around that. Like we can sort of trial feelings and genres and like, let's say you want procedurally generated music. You can do that with GANs and take in all these different factors at one time. It's really cool. If you're trying to do text to speech, some of the earliest, Macs, I think there was like the say command on the terminal there. That was very like firmly policy driven, where the creators of that didn't use machine learning. They basically enumerated how each of the letters and syllables should sound. So that was definitely AI, but it wasn't machine learning. Now modern data synthesis can take in, sample audio from, native speakers of different languages. And even if we can't necessarily classify what makes a certain accent behave in the way that it does, the algorithm doesn't need to understand that. It can find the numerical representation in the audio data and then apply that potentially in the creation of new data or in the creation of new audio. So lots of really exciting opportunities here. Okay, tools of the trade. This was one that I saw a lot of interest around. Sorry, I'm speaking very quickly, so I need to drink some water. Cool. So I only have one slide here, but there's a bunch of other stuff I'm going to talk about at the tail end. But I think that these are probably the most sort of tangible to you as users if you're going to design and build AI and ML systems. The first is frameworks. So much like, let's say, React or Angular, abstract a set of primitives to make it, you as an end engineer, make it easier for you to build these complicated systems. Frameworks did this exact same thing for machine learning. If you look at a lot of the research papers that come out, there was a big, like way back in the late 90s or the mid to late 90s, deep learning and like machine learning and AI and algorithms that we talk about today were implemented, but oftentimes every single researcher and engineer implementing them was implementing them from scratch. You know, like think about, I don't know if you've taken like a computer science course, you may be implementing multiplication and division from primitive operations with the register, with like addition, and even subtraction is just addition with a negative sign in front. Like that is the level of abstraction that machine learning frameworks existed in, you know, pre-2000 largely, and that's a very hand-wavy sort of time frame. But there's two main things that caused the explosion of AI and machine learning in the way that you see it today. One of which is the feasibility of cost-effective compute. This is like largely like cloud providers and hardware improvements. I'll mention that at the tail end. But the thing that probably matters to most of you, so that you actually have the ability to spend time building something like this, is frameworks. So don't worry about bit flips and those very sort of like low-level operations. Think about things like neural networks. What are the layers I want to add? Can I sort of declaratively add all of these layers to this network? Or in some examples, if I have if I have an algorithm that has a discrete start and end, like a logistic regression or a linear regression, why can that not be abstracted to a simple method or a simple function that takes my data as an input? And so a lot of people had that exact same thought process. And in the effort to actually make it easier to advance in the field, a lot of these frameworks are born particularly out of the academic community, but have moved to companies that have begun productionalizing this. So TensorFlow, as we see it today, is actually a really good example of this. Theano was the very early form of being able to abstract over some of these operations that were not even, let's say entire layers of neural networks or part of these, machine learning algorithms, but just some of these primitives, so that you wouldn't have to deal with, like GPU operations. You could, start to script this. And then we get to something like Keras. Keras came out of Theano and sort of like two opinionated approaches, and Keras sort of reabsorbed and was the migration of Theano at one point. There's someone named Francois Cholet. I don't know if I'm mispronouncing his name, but he's now at Google. And so the Keras was very well known because its APIs were very easy to understand for developers. And in the beginning, there was sort of this there were kind of two communities. There was both Theanos and Keras, even though the same person that worked on Theano had written Keras. And eventually, the Theano operations had gotten sort of absorbed into the easy to understand Keras APIs. Now, all the while, Google internally, I don't remember the timeline of Francois joining, but TensorFlow was this internal framework. I don't know if it was called something different before they released it, for Google to perform machine learning training and primarily training internally. And eventually they open sourced that. And that was, I don't want to say it was like great leap forward, but it very much jumped onto the scene as a huge step forward, where the tooling largely in the community had not existed to that same quality. And this brought the ability for everyday developers that had not dealt with AI or ML or had not been PhDs or academics to be able to start performing machine learning. Now, as we fast forward to today with TensorFlow 2.0, this has been a substantial jump in and breaking changes in how TensorFlow has made, but largely, as many would say, for the better, but I guess that's sort of up for debate. This Keras eventually became sort of folded into TensorFlow and TensorFlow 2.0. Now the models around how TensorFlow and TensorFlow 2.0 work, there's largely two camps to my understanding. You have the DAG, the direct acyclic graph, where you sort of define your entire graph and then you run that. So you have a series of tensors, which are just n-dimensional vectors, very mathy sort of explanation. But TensorFlow got its name because you would have these n-dimensional vectors that could be stacked next to each other that form a neural net, or your data simply gets processed in this sort of like iterative fashion, and the data flows through those different tensors. And that's how TensorFlow got its name. Fun little fact. And if you actually watch an execution graph of the DAG, the direct acyclic graph, it actually looks like water flowing in from the top, and then it trickles throughout all of these different parts of the graph. And then sometimes it comes back and it goes down for a certain amount of times, and then it pops out at the other end after a certain number of epochs with your model. TensorFlow 2.0 implements some other quality of life changes. Many will consider improvements, but they're just different. They involve the idea of like eager execution, and this changes sort of how your graph or your training process is compiled. It offers some other improvements that you were not able to get with the DAG, like defining a variable number of epochs that you could train your model for, and without having to hack it a bunch, and so on and so forth. I'm not going to give the full, nuts to bolts equivalent here with Torch and PyTorch, but TensorFlow is the most prevalent one, I would say. So I think it's really valuable to sort of walk through that history. Torch and the evolution to PyTorch is actually very straightforward. Torch largely came out of the academic community also. And when you think about machine learning training, I haven't gone into this too much, but machine learning uses GPUs in its training. Now, the difference between GPUs and CPUs are largely that CPUs are optimized for single or a very small number of essentially serial processing. Imagine this queue in this line, and you want to blow through all of those processes or events in that queue as quickly as possible and ensure that that queue never stacks up. Now, a GPU is a piece of hardware that performs computation with a different level of optimization. Instead of trying to blow through the single thread as quickly as possible, or the single execution stack as quickly as possible, the goal of a GPU is to be able to blow out the number of cores, scale it out so that you can perform operations that are inherently parallelizable much quicker. So an example of something that's parallelizable, if I wanted to give you a book and say, can you count all of the, or let's say it's a PDF, right? So we're all in digital format here. Count all of the A's in this book as quickly as possible. Now, the most like rudimentary way of implementing this would be to sort of just scan down every character in the entire book, and every time you have A, you increment 1. Trust me, there's no like comp sci interview trick here with like dictionaries and all of that. It's fairly straightforward. So that's the native way to do that. And on a CPU, that would be really the quickest way to do that, let's say. But what if I propose that, if every section of that book, if I took the A from every one of those chapters, let's say, and I counted each of those chapters and I just add them all together, that gives me the same total as if I just went front to back. Now, the only problem is, well, how do I count multiple different things at the same time? Bam, that's a parallelizable problem. To make that a little more broad, essentially any class of problem where you can perform compute on one part of the problem without needing the result from another part to perform that computation, i.e. I don't need to know how many A's are in chapter 1 to compute the number of A's in chapter 2. I can spread this problem out across my GPU, have each core on my 300 core GPU, for example, calculate like one page and have the computation done very, very quickly. Now, that is what has happened under the hood to perform a lot of machine learning training, and wrangling with GPU firmware and middleware is really, really arduous. And it's just something that like you don't want to deal with, right? You just want to be able to write code that passes you and your data to a model. Now, Torch came out of the academic community and did this. It was another machine learning framework, and it did this for Lua. But a lot of people don't know Lua. And so, people wrote CLIs, and Torch was available as a CLI largely to make this possible in an SDK. But that language barrier didn't really meet developers today where they are. There's far more developers in Python than there are in Lua, I would say. Now, why Lua to start? Well, Lua actually is a very common programming language for scripting in game engines, in video games. And if you're probably thinking, well, before Bitcoin mining and AI and ML, who used GPUs extensively? Well, it was video game designers. And so that set of like middleware was well understood by that sort of community and had support for Lua. So Torch was first implemented there. But then I believe Facebook eventually picked up the open and supported the open source project for PyTorch, which came out of Stanford's academic lab. This trend of like academia improving on algorithms and then that being released and sort of adopted by like and having financial backing from big organizations and companies is a pretty consistent trend. Now, both of those are very ambitious. They try to take on these like, huge problems of making it easier to use machine learning and AI. And sklearn has the same mission. sklearn stands for scikit-learn. It is a Python library, but it has expanded to do so many things that I hesitate to even call it a library at this point. I'd, like more likely call it its own framework onto itself. But largely the interface with using sklearn is much more pointed and leans away from things like deep learning and neural nets in the way that TensorFlow and PyTorch do, and aims to deliver on that concept of you want to use X algorithm, it requires your data and your hyperparameters, just pass those in as one method call, and scikit-learn handles the rest. So again, trying to optimize for developer experience. I know developer experience can be hard to quantify the value of, but ultimately we've seen the value of it firsthand. Developers now use sklearn as their first framework in droves in ways that they wouldn't be able to necessarily for TensorFlow or PyTorch. One of the other things that scikit-learn does under the hood is, it's a Python package. Scikit-learn actually can compile your Python code down to C code so that it is more performant for these computational operations. So oftentimes you'll hear these debates on Hacker News or Twitter. Sorry, I'm picking on them, but like that's where these things typically happen over like Python is air quote like an inefficient language. Well, at the end of the day, if efficiency is defined by the amount of time it takes for you to ideate and then deliver software, who cares if your code takes a little bit longer if you can deliver it way quicker because you can write code faster? Well, a lot of people do care about that because at the end of the day, what if you could have both? What if you could have an easy to use language that folks know at your company like Python? And what if you could have the low level efficiency of a language like C? And scikit-learn actually does a lot of this under the hood, and it was a very quiet sort of set of releases, but decompiling your code sort of completely invisibly, completely magically to write in Python and transpile to C made this really cool. So that scikit-learn evolved from just this like workbench library that people would train their first model on to something that actually performed at scale and wouldn't require you to sort of graduate to a different framework tool. But one of the prevailing trends, I think, across all of these frameworks, whether you're dealing with TensorFlow and PyTorch at sort of the neural net deep learning level, or scikit-learn and some of these more driven, more pointed rather, algorithmic packages, is this consolidation of APIs. In the early days, it was sort of like the Wild West, and whereas AI and ML was exploding in popularity, people were able to use it. Maybe folks chose a framework because the tutorial they saw on the internet for what they wanted to do used that. The field has matured a lot since then. And even something as subjective as developer experience, something we all may want slightly different things, I think a lot of the maintainers of these projects have realized that this idea of like folks that are working with ML and AI tooling often by default don't want to mess with the underlying primitives, but they want an opt-in ability to change them if they so desire. So examples of this would be like in either TensorFlow or scikit-learn, like I don't want to have to define all of my hyperparameters. Let's say there's a set, like maybe I don't understand hyperparameters, right? What is a good value for, tree depth in a, like a bagging tree, or like what is a good value for number of epochs? I don't know. Maybe I'm a new developer. This idea of like sensible defaults started to get baked into all of these languages, where you can still have this very simple, like give me my data, declare what algorithm I want to use or what neural net architecture, and then take care of the rest as best as it would. But you have the ability to go in, and as you grow, mature, and perform experimentation, you don't have to jump to another framework. You can then start fiddling with the knobs under the hood. And in this way, a lot of the APIs all start to look very, very similar. And this was actually why Keras got entirely folded into TensorFlow, because they were developing independently, and eventually their APIs looked so similar that I was like, why do we have two frameworks? We might as well just meld them together. And I think that this is at a point where like those steps I defined before, and we'll see in just a moment sort of in production, but largely like the declare my data, declare my algorithm, declare my configuration, now run this function or this algorithm that takes in my data, takes in my algorithm, takes in my config, and just spits out my result, my model file at the end. That's something that you see consistent across almost every single algorithm and framework today. Okay, without further ado, open source packages make this possible. And a lot of these open source packages are actually used by these frameworks. And I didn't mean to exclude the word open source up on frameworks, because a lot of those frameworks are also open source. But in the same way that I said sklearn under the hood can transpile down to C from Python, that was not necessarily all the work of the sklearn team. Some of these primitives like pandas, which is sort of this data frame and number manipulation framework for tabular data, did that under the hood. And so when sklearn uses pandas, the end user of sklearn gets the benefit from that. There are some even further and deeper improvements for more pointed use cases like Dask and Rapids from NVIDIA. They're like hyper optimized versions of pandas that can run certain operations on the GPU. So again, even the companies that are making, let's say, low level infrastructure like GPUs recognize that people shouldn't have to interact directly with it. They want to make it possible through higher level APIs. Things like Seaborn for visualization. I know there's many others, Matplotlib or Plotly or whatever. Are all like tools that would be able to generate visualizations like we saw before that help with sort of like the understanding and the observability. But they're not as much prescriptive out of the box. You need to understand really what you're trying to do with them. Again, think of those more like the shovels. Whew. Okay, so this is sort of a blank slide for future. There's a lot we can talk about here. I'm going to pop back up to 4, which was AI ML in production, because there's a lot to go through here. Swap the slides, take a water break. Okay, cool. So, you know, all right, Nick, I've got it. I understand a little bit about how modeling data works. I understand the names of some of the tools I'll probably use and sort of the history around them. But, you know, like, how do I get from me to Airbnb's data science team, right? That's probably the next step we could talk to. And that's very much like the 2-step draw the owl. Step 1, it's like the rough outline with like the sketch. And then step 2 is just the whole owl. But I think that there's a lot of like forks in the road here that will make it much clearer why there's no one size fits all or prescriptive solution for AI ML. But that's for good reason. This slide is, the colors are not the best, so I apologize for that. I promised I wouldn't sort of, you know, tailor this to specifically Amazon or AWS services, but this level of abstraction is something that I have found that is consistent across users and companies that are trying to do AI ML. So ignoring the specific names of the services on here, I see this 3-tier system being very, very, very consistent, and I'll talk about why. First, the top, we have the most abstracted. Imagine an API that you vend like a SaaS solution. So if you've ever been to a hackathon and someone's sponsoring and you're using this API for the first time, you don't have to worry about how any of it works under the hood. You just know that if I pass in this data, if I look at these docs, this is the behavior I'll get on the other end. The most sort of white glove service, that's AI services. Now, one step down, you have ML services. The way I like to describe these is like, okay, I accept that, I have a problem that maybe isn't very common. There's not going to be an API out there for me. I want to train my own models. Maybe I need to be able to scale up, scale out. I have a ton of data in production. I'm evolving from experiments. Services that make this easier to do, sort of like handhold you a bit and like abstract some of the really ugly underlying stuff. That's sort of that middle tier. I see a lot of companies in the middle tier and maybe one of the largest for like some of their custom problems, but we'll get into that in a moment. And then the bottom layer here, actually, ML frameworks and infrastructure. This I see as a predominantly small part of the overall amount of developers, or it's developers that start out here who work directly with some of these primitives. And then if they're like escaping the experimentation phase or they're trying to scale up, they may move up one layer in the stack to sort of this like, abstracted ML services layer. So a good example, we're gonna start at the bottom, we'll make our way up. So here in the bottom, ML frameworks and infrastructure, this involves a lot of the things I just talked about, right? Like TensorFlow, MXNet, PyTorch. These are frameworks. You interact directly with them. Gluon and Keras, I mentioned before, are sort of like abstracted interfaces on top of some of those frameworks or consistent experiences. But let's say you write some local code. Let's say I have my dogs versus cats example, and I have 100 images. I can run that locally on my laptop. But let's say I want to roll this out into production at my company. Maybe I have an app that's like, just like it's just like a fan site for dogs. No cats allowed, right? I may have this data set of like tens of thousands of cats and dogs or images. Now, realistically, I don't want to set my laptop on fire. And even if that seems like hyperbolic, the point is that like that level of compute may not be sufficient for running that in a reasonable amount of time. That may take like days or weeks to run that model. Let's say I have 10,000, 100,000, a million images. So this is where you sort of outgrow your small data set and you want to scale up and out. And this is where cloud infrastructure starts to become valuable. Now you can rent, virtual servers sort of as is off the shelf if you want that same experience. But a lot of the cloud providers or even like middleware SaaS platforms that like data science platforms is often what you'll hear them referred to. Think of like H2O AI or like, trying to think of some of the other ones. Data IQ. There's like a whole bunch of like these are typically targeted data scientists where you have your code, you want to write this like low level model code, but you want to abstract away a lot of the underlying infrastructure. That's where you sort of graduate into there. And this can help you with things like those sensible defaults and some of these like opinionated takes from your infrastructure provider. AWS is one example of that. We offer something called SageMaker that basically does all of those things that you see in that layer. Because when it comes to building your own model, there's a lot of steps. We'll see them in sort of non-ML or non-AWS terminology in just a second. But the reality is that with ML services and any of this, you don't get value until you deploy a model. So you can train a model, you can deploy it to this massive GPU cluster, you've got your result out. it's not serving inferences, you're not getting value out yet. You need to be able to deploy that as an endpoint, and then you can start serving requests and then, you know, returning that investment. Now, lastly, but definitely not least, is this top level AI services. Think of these as problems that are generalizable. Now, I know every company works with a very particular set of subject matter, so you may not think like, I need to forecast, you know, energy at my company, or the amount of like, you know, like, I don't know, like Crocs slides to stock in my factory, right, for the summer. That maybe seem like a very pointed problem, but the underlying ML problem is actually simply numerical forecasting. Now, your data set is unique to you, but ML forecasting may be available as an algorithm. We have that at AWS, the forecast. I'm sure there are equivalents elsewhere. One of the ones that I think a lot of us have probably dealt with is, you know, this concept of facial recognition, right? So, you know, if we want to be able to determine like, does this face belong to X person? Now, everyone has their own face, and there are easy ways for systems to be able to basically like register a face or like a dog or an animal or something, and then return yes. The fact of the matter is you may not need to perform that like intricate training and expensive training step over and over and over again. Another example on the computer vision front would be something like the world around us, right? Like if you wanted to build an application that sort of just understands the content that's in an image, ideally an off-the-shelf service provider for something like AI services would be able to have a robust training set that included lots of different types of dogs, lots of different types of cats, you know, like cars, so on and so forth, so that you don't need to reinvent the wheel and inherit those training costs. You could simply vend one of these off-the-shelf models and be able to receive that. Now, you know, if their model didn't include labels or objects that you really need for your use case, that's when you'd move down the stack to something like ML services. So I know this is an AWS slide. Conveniently, a lot of the AI services at the top are like fairly intuitive to what they show. If I have time, I'll show you a demo of some of these that I wrote to basically showcase what those are capable of. But these are largely the three tiers of customers that I find, and they coincide. Customers largely, even if they're in the middle, start to gravitate based on their problem constraints to one of these three tiers. And then AWS has gone and built services to serve each of those tiers, but the abstraction is consistent. Cool. So I know that was a lot about the landscape, but I want to make training a model really, really, really easy for all of us to sort of understand. So the example that we're going to walk through here is going to be, let's say I have players in a video game, and I'm a game company. I want to detect cheaters, and I want to be able to then, let's say, punish them, and I don't want to punish non-cheaters. Let's say I have a past data set of all of the people that I've banned that I've confirmed have cheated, and I can label each of their cases and some of like the server data that they were like running too fast in the game, they were cheating or something, right? So we're going to talk about that scenario in the lifecycle of Toast. This example will extend beyond anything that is a binary classification problem. So anytime where people fit into either class A or class B, it could be cheaters, non-cheaters. It could be credit card transactions that are valid or not fraudulent, or fraudulent, so on and so forth. So we're thinking Toast. Now, why Toast? Well, there's a bunch of different parts, and I think that the analogy lines up well. So when we think about all the different parts that go into, or the different states that toast exists in before you inevitably eat it, you start on the left side with wheat, then it gets sort of pulled from the ground and processed and milled into grain. There's some sort of further processing and cooking process that makes it bread, and then we ourselves sort of put that in the toaster and then make toast, right? Now, that state doesn't change magically. There's a specific process by which each of those things undergo. I can't just process wheat in the same way I processed it into grain to make it into bread. No, it's a different process. It's called baking, and then so on with toasting. So there's a specific process for each of these to change our raw material into the processed product that we want inevitably. And this is actually the same for machine learning. So we start with raw data over here on the left-hand side. In the example of players cheating or not cheating, let's say that we have this data from the server of them like running around, and it shows their locations and all of this, and we need to clean that up. Let's say we have a bunch of data in there that we don't care about. We want to cut that out because that's not necessary. Let's say we want to add a bunch of features. Let's say we want to say like, okay, well, player's speed may not be something that I record in my actual game state, but I want to derive that feature because I think that player's speed is indicative of whether they're cheating or not, and I want my model to know that. So that's where we're going to get into something called feature engineering. So we transform this clean data. One example of transforming it would be data augmentation. Now, augmenting data can take a few forms. It can be either adding features to existing data to sort of express or give our algorithm a better shot of trying to surface the phenomena that we are trying to recognize, or it could be something like the class imbalance problem. Machine learning algorithms behave in very particular ways when you have imbalanced classes. So like in the fraudulent example, the credit card, or even in this example, let's say cheaters are a very small percentage of our population. There's this concept called generalizability in machine learning. You can overtrain and overfit to your model, to your data set, your training data set, such that the model will always recognize the behavior on the exact data points that you fed it, but then it doesn't generalize well to other similar data points that it should be able to get to. Now, by augmenting our data set, by essentially taking, in this example, adding artificial data points that are basically like fuzzy matches of our existing cheating population, the idea here is that the plane that is generated by the model on that decision boundary is actually representative of, other ways that players can cheat within that known set of boundaries, so that like augmentation. And this is where feature engineering comes in. I'll show you what that looks like in sort of raw form in a second. And then lastly, we're going to pass in those engineered features, with the labels, into our algorithm that trains the model. So in the same way we go from wheat, this very raw material that just comes out of the ground, to toast, a finished product, we do the same with our raw data and arrive at a model that can perform inferences for us. So let's take a look at this. So this is a little bit of minutia, but if we start with raw data, like let's say your game server just does something like prints out the position of your player every time they make an action, right? This is the raw data that can come in from our server, and this gets generated not knowing what we want to do downstream with this. So instead of duplicating, and creating new data in sort of parallel, what we would rather do is we'd rather pre-process that and make that into clean data. So we think of data in like tabular format. Let's say we have the change in X position and the change in Y position and the change in Z position from the previous value as a way that we can sort of assess like, oh, wow, did the player move more than they should have been able to? Well, our model will pick up on that with this piece of data now. This is where you start to get into the weeds a little bit with custom feature engineering. And this is where if your problem is not common, you will likely spend a lot of time and experimentation on. And this is a lot of the secret sauce of developing accurate algorithms. A lot of the time, the hard job you have as an engineer is trying to come up with ways to quantify the features and phenomena that we as humans can see in a data set or in a problem. Like, oh, that person's flying across the screen. Well, how can I generate data or derive that data such that my algorithm will figure out the numbers and the thresholds, but I need to be able to provide those as features so that it can figure that out. That feature engineering process is often where you'll get the most bang for your buck and where companies generate their secret sauces. Just knowing that you use algorithm X, like XGBoost, is not enough for you to just simply copy the implementation that a company has. The feature engineering and the data that they have are a big part of that moat. And then lastly, I know a lot of folks refer to machine learning as a black box, and we have this last little arrow here for training. So, here we have our little black box, but I want to give you a little bit of insight into how that works. So the toasting process with bread is pretty straightforward to all of us. We put bread in, that's the input. We have our box, our device, and out we get toast. And on that toaster, we have a bunch of dials. Now I know toast doesn't usually go in like it's like on an assembly line. Usually you just load it in or top load it or something. But we can actually set a lot of these knobs and dials so that we can get toast that comes out the way that each of us wants it. Some people like the toast darker and crunchier, some like it, lighter, what have you. And we can arrive at that output of like that quality of the toast by changing a bunch of different knobs. You can change the temperature, the duration. Maybe there's it's a really fancy toaster. You can change the number of coils to like disproportionately heat like the middle and the sides of it, and so on and so forth, right? Like maybe you have even just something as simple as those two first dials, but these are your hyperparameters. You have this process by which raw ingredients put into the toaster, and the process is simply, it will heat it with this configuration for, and then it will give you the output. It'll just pop it up, right? Now, this is not very different in any capacity from machine learning. So our raw data is our input, or our cleaned data, let's say, if we engineered some features. And at the other side, we want to generate that decision boundary so it can perform inference on new unlabeled data. But then we have this, really scary bit here in the middle. So this black box is essentially our algorithm. Now, each algorithm has its own trade-offs, much like, a bunch of different toasters probably have their own trade-offs. like energy efficiency, what have you. But all of the knobs on your ML algorithm are your hyperparameters. So in the same way that like you can change the duration that will affect literally how long it takes for your toasting to complete, amongst other things, the same thing actually exists with machine learning. You can change the number of epochs, which is essentially the number of cycles your your algorithm applies to your model output, to change that, and that linearly is proportionate oftentimes with the amount of time it takes to run. You can change like maybe something algorithm specific. Every algorithm will have its own set of knobs you can tune, like in a decision tree, the max tree depth, or something like XGBoost, max number of features, the minimum sample split when you do training and test splits. I know each of those is very nuanced and requires a lot of further explanation, but if you think of this toaster analogy where you have bread input, toast coming out, and you've got a lot of different ways by which you are telling the algorithm how you want it to alter that with very simple explanations for each of those hyperparameters, you can start to surmise how you'll experiment with this machine learning training process. Okay, so that was training, and I've said previously that you need to be able to perform inference to get the bang for your buck out of your experimentation. You can have a model sitting on the shelf after your training that you think has like 99% accuracy, but again, it doesn't deliver value until it performs inference. So we're going to walk through this. I've abstracted the AWS services away so that it's as broadly applicable as possible. So let's say you have some sort of application. It will develop data in some capacity. Now, if you followed sort of like microservices principles, or like just the understanding that like your compute may need to scale up separately from your storage, you may want to move files to long-term storage as you grow your application, or as you want to make sure that that data remains durable and you have access to that in the future and that it doesn't disappear. Let's say a server goes down, right? You don't want to lose all your data. That would be a really bad experience. So you move your data on some regular interval, or let's say you do it event-driven so that every time it's generated, it moves off to long-term file storage. Now, that data may be used in other parts of your application. Maybe that's a database. Maybe that's some other stuff. But here we're just talking about the machine learning pipeline. So that's from that same long-term file storage, you may want to do that pre-processing. So let's say from all of the data that exists, maybe you don't care about a lot of the features or a lot of the columns in tabular data. For your machine learning experiment, you only want a subset of that, or maybe you want to augment features. You'll do ETL, extract, transform, and load that data, perform that processing, and then put it back into long-term file storage somewhere. Even if we only keep it there sort of temporarily. Now, there's a few ways to go about this, but ultimately, if we've trained our model, we know sort of the parameters that we want to perform inference on. We can set a trigger, and this is going to be a little platform specific here. But let's say that we have a trigger in this folder over here, where every time a piece of data hits this long-term storage after it's been pre-processed, I want to perform an inference on it. So every time a user uploads an image of my app, it goes to long-term storage over here. I perform ETL, so I like strip it down of like unnecessary data. I put that into this sort of trigger bucket, and then every time an image comes into here, bam, I want to perform inference on it. And this can be an event-driven compute layer. Think functions of a service in AWS world, that's AWS Lambda. So, all of this to say, like, you didn't need to provision extra infrastructure to passively sit there to perform inference. You can do that in sort of this event-driven way, and that's a broader conversation for another time. But it's a good way of tying costs to exactly when you're performing computation. Now, I think this next step here is a big, like, fat optional section. But a lot of people talk about this idea of human in the loop. Human in the loop often comes into play with this idea of, I have a model, but let's say I am never comfortable fully automating the decision-making process or the classification of data for my machine learning system. Now, one of the things you can do is you can conditionally route data. You can, there's an AWS service that does this. I'll show it in a second, but largely this idea of like, AI returns a confidence interval or confidence value for an inference. What if I could have a scenario in which, I want to say, if the algorithm is 90% confident that's a certain classification, I'm happy with that confidence. Please automate the response there. But if it's lower than that, I may want a human to review that. That way you get sort of the ability, you get the best of both worlds. The human can review instances where the model is not confident. Think of these things you may not have well represented in your data set. But you can also automate all of the easy predictions, let's say. Let's say, for example, some cats and dogs look very similar, certain breeds, or the picture is hard to differentiate. Now, that would be a prime example here, even in a very basic scenario. So what that looks like is basically you have this proxy for your API, you hit your endpoint, and then based on the decision or the confidence value of the prediction, if it's confident, bam, you can say, all right, yeah, that's 95% confident. That is definitely a dog. Or you say, okay, wow, 65% confident. I don't know. I don't want to trust my model to automate this one. Send that to human reviewers. And then that their label goes into that action or resolution. Now, traditionally, this is something that's you just need to write additional infrastructure code, and machine learning developers that skill set is fundamentally different from operations, from ops code, and cloud computing broadly, and writing application code. They're all different skills. So you could do this manually. AWS has a service for this called AWS. I think it's ground. There's a certain sect of ground truth that enables this. I'll show that in a second. But notice that all of that is contingent on having labeled data. And I mentioned that in the beginning, that if you move from unsupervised to supervised, where you want to automate the classification of certain pieces of data, you require labeled data. Now, I mentioned a very, very simple scenario before where let's say I have this 100 image data set or 1,000 image data set. I can just drag them into 2 different folders on my computer, throw that into my manifest. But the reality is that if you have a big trough of information, or you're a company that has a lot of data, you need like a more systematic way of doing that, right? You can't just have like a Google Drive folder where you tell a bunch of employees like, hey, go on and just like take 100 of these and drop them into the right folders. That doesn't scale out well. It's super hard to manage. Like, how do you manage permissioning around a lot of that? And as soon as you start dealing with a machine learning problem that is where the labeling is more granular than just like, is this class A or class B, you start to run into problems. At AWS, we saw that this was a problem with a bunch of people. And largely, like, this problem is in many ways like starts to become gamified, right? If we could gamify it, that would make it a lot easier to deal with. So I mentioned before binary classification, yes or no, or cat or dog, for example. That's one type of problem. Now, in this scenario, we don't see cat or dog. We see, like something that says draw a box around each flower. Now, this makes a lot of sense, right? If you've ever seen OpenCV, for example, Open Computer Vision as a library or a framework, or even just this problem simply, let's say you wanted to auto crop. You would need to be able to identify where in the image a certain thing exists. So now our label is not simply class A or class B for this image. You will actually have, if we have a box, you will have 4 different coordinates for the corners of this box to define that. Now, if I have an image and I'm working in this manifest, like I'm literally going to type out like pixel, like a tuple of pixels, right? Corner 1 is at XY location. Corner 2 is at XY location. Corner 3, XY location. Corner 4, XY location. And that visually would define a box. But wouldn't it be so much easier if we could just like drag our tooltip or drag our cursor over it and like make a box on hover? And like that's the experience that everyone would want, right? So that is available through SageMaker Ground Truth. But ultimately, this makes it just significantly easier to start to draw this. And companies have like gone and every company before a tool like this has released, like they have to go and make this tool themselves. Sorry, I promise I'll get off the AWS soapbox very quickly. But this is just, having labeled data is one of the biggest blockers to actually being able to access any of the stuff I just taught you. And I know it sounds like such a trivial problem, but the tooling there did not evolve actually in the same way that some of the frameworks have evolved, which sounds so counterintuitive, right? It's like the much harder problem got solved before some of the much easier problems. But sort of as reality may have it, that was the case. Now, when we start thinking about examples like self-driving cars, I talked about reinforcement learning before. This problem may become even more granular, right? You have these like extremely high resolution cameras and you need extreme precision, right? It's not okay for me to just highlight this flower as a square and then be done with it, right? Like if I'm a self-driving car company, I want to know every pixel on that screen that constitutes another vehicle, right? I don't want to just have this like big blob around it. And so that may be something like semantic segmentation. I want to know within this given image, like where are the blades of grass? I want to highlight every single blade of grass, and I don't want to just have this, like big rectangle around it. Semantic segmentation. Oh, sorry.
I was going to say, I just want to give you a time check. So it is 7:30. So I just wanted to give you kind of a warning or direction if you wanted to have some time for questions as well. So
yeah, sorry, and I didn't think that this would go on as long as this did. I apologize, but I'm also super close to the end. So yeah,
perfect.
essentially SageMaker, Ground Truth, and similar tools like it that exist out there help you to label that data because depending on your problem space, again, it may not be tractable or reasonable to label by hand manually all of these things, and you can distribute your data sets to other people or people within your company. Let's see here. Here's a reference architecture. We'll blow by this. We covered 2 already. So the only things that we didn't get to were 5, which is future. This is some of the more current events around AI and machine learning, things like GPT-3, which was really cool. If you guys are really interested in that, I'll let you ask me that. But I want to be respectful of all of your time. I also have something I have to run to in just a little bit. Before we get into Q&A, I will sort of preface this. Thank you for the ability to get to talk to all of you. I'm really happy to get to talk to really inspired folks like yourselves. I know that this talk is very much a shotgun style, but I hope that, I'm super receptive to giving you personalized feedback. I know I made that clear at the beginning, but reach out to me on Twitter. My email, I'll leave it in chat as well, so that you can ask me any of your own personalized questions. But thank you so much for this opportunity. And I hope you were able to learn something regardless of, what your background is. I figured I'd open up now to Q&A. I know I haven't seen stuff in chat, but I'll let people run open mic. I'll let people ask questions in chat, whatever your preference is.
Yeah. Can I ask a question?
Of course.
Yeah. Thank you, Nick, for the wonderful demo. Just wanted to ask, so I'm working with a startup that is deeply involved with computer vision with respect to the football game. So, you would want to use the computer vision for determining the location of the players, tracking of the players, the football, and then calculating things like the speed of the ball, the speed of the players. And we wanted to use the AWS like SageMaker and then recognition. So how do you think that which particular services could we actually use from AWS that can really help us out with the machine learning part? Whether it's with the analysis of the video and then, finding out the metadata and the metrics.
Yeah, great question. So inherently in football, and I guess in America, and that would be soccer here. But actually the problem is no different largely from an ML AI perspective. What you're largely talking about there would be computer vision. Assume that you're assessing and analyzing video data, or let's say image, if it's just like a static position, to be able to derive insights about the match. You could get really crazy and incorporate like sensors on the players. I know like American football and the NFL has stuff like that. But AWS actually does this with Bundesliga. I don't know if I'm completely butchering that pronunciation, but they do that exactly through Amazon SageMaker. So the same problem you're trying to solve, they work with that too. So essentially, what that would look like as a pipeline is that you would have historical data sets around the video. You would store that in something like Amazon S3, long-term file storage. You can then mess around in a Jupyter notebook hosted with Amazon SageMaker, and then you can find ways using those computer vision algorithms, or maybe let's say you're using like TensorFlow, for example. You want to predict the likelihood of a shot on goal scoring based on, let's say, intrinsic data on the screen, right? So you could say like, all right, well, I want to know the positions of all the players. You can use computer vision to assess that. You augment your data set, and then you could perform that calculation of likelihood of shot scoring based on where the ball is and all of the players. And then you can compute that, let's say like every 3 frames or something. You could have it in like pseudo real time, sort of like chance a goal will be scored, right? And you can make your own arbitrary scale around that. But SageMaker would do that. You would train your model with SageMaker. It would pull the data from S3. You can deploy an endpoint automatically with SageMaker. And then you essentially get an endpoint that you can ping. I think you do it through the SageMaker SDK also, but it makes that real easy. And you just substitute, you inject, image data that would be pre-processed in the same way before you trained it.
So just one like follow-up question on this was that, so let's say that we're trying to get the data from the SageMaker. So we're using the intrinsic data that you said, that all our videos are getting stored on the S3 bucket. So let's say we import that over. Now, let's say, because, the most important concept for us would be to find, the accuracy in getting those goals on target, as you said. So can we just use something like the AWS recognition for, let's say, detecting the players and the ball? I mean, not using TensorFlow and let's say ImageNet to detect the players, and just using, let's say, PoseNet and other such TensorFlow-based libraries to get the rest of the calculations. So is that possible? Like, can we just use like an endpoint that just first detects? Because I guess AWS recognition is quite powerful right now, so it can easily detect the players as well. So can we just use that as an endpoint to sort of make our entire AWS SageMaker code that we're writing, the custom code that we're writing, a bit simpler?
Yeah, totally a good question. So to give a little bit of context here, this complex problem actually has a lot of different parts of the ML pipeline here, right? So for example, in the scenario that I described, like what is the likelihood given all the player positions on the field of them scoring a shot on goal? Well, you needed to figure out where all the players are on the screen, which is a computer vision image recognition problem, right? So you actually break down this problem that is, your input is an image or a video, and your output is like likelihood of shot on goal, and you break it into like the computer vision part, which something like SageMaker recognition or recognition video could help you solve. And then with those data points about where the players are on the screen on a given point, then you may have like a mathematical model that gives shot on goal based on all of these parameters. I actually linked in chat a link to the deep dive on the Bundesliga model that includes some of the parameters that they use. So things like distance to the goal, angles to the goal. I mentioned before feature engineering, like has the player just beaten an opponent? That's something you would augment into your data set, for example. So that will provide, I think, like a much deeper dive on that. I just want to make sure that I can get to other people's questions too. So we can circle back around if we have time.
So is it possible to connect with you later just to probably have a discussion on this?
Yeah, sure. I'll give my email and Twitter in chat.
Thank you very much.
Does anyone else have any other questions? All right, doesn't really look like it. But we can leave it at that, and you guys can connect, offline and continue that conversation if you so like.
And just one last question which I can take.
Yeah.
Yeah, I just wanted to ask, like, do we get the ability to, like, let's say, choose the kind of GPU with SageMaker? Like, let's say I want a more powerful GPU and we can like pay for it, but is it possible to select the computation power?
Yes. So I'm pulling up the link as I speak. Essentially, with EC2, if you're familiar with that, virtual servers, managed servers through AWS, there is an entire slew of different configurations you can choose from. Largely, they are I believe it's the P class or the G class instances that you'll want to look at. But essentially, any sort of consumer and commercial grade GPU that is available and is cost effective is available on its own type of instance. So like P3 instances, there's the P3 2x large, 8x large, 16x large, so on and so forth. All of the stats are available on that page. So you can, just like you said, declare that. Now with SageMaker, it makes it real easy. When on training time, you can simply pass in the instance type and the number of instances. And as long as you're using a built-in algorithm, it will actually automatically provision all of them, distribute your training workload, and spin them down when it's done.
Thank you.
Yeah, no problem.
Perfect. We can call it kind of a day for now. Thank you so much, Nick. You're getting some thanks. That was really informative, and some additional thanks from our fellows. So thank you for taking some time out of your day to really spend some time going over this with our students.
Yeah, no problem. Thank you for having me. Again, I was an MLH coach. I was in similar shoes to many of you. I've been on the ground at startups before. So like I said, it's a pretty broad topic, but I hope everyone walked away with something useful. But please, please, please don't hesitate to reach out to me. Amazon quite literally pays me to help people like you solve these problems, so don't feel bad about messaging me. I'm literally on the clock to do that type of thing when I'm not giving this talk exactly. So thank you again. It was a real pleasure.
Awesome. Thank you so much. Have a great night.
Yeah, have a good night, everyone. Thanks
Bye.
again.